Imagine for a moment floating in utter darkness. No light, no sound, only the infinite weight of gravity around you. You drift toward a point of no return, where time warps and space bends, and even light itself cannot escape. Welcome to the mysterious realm of black holes. Tonight, we explore the most relaxing facts about black holes to fall asleep to. Let your mind sink gently into the cosmic deep as we uncover the silent wonders of these dark giants. What exactly is a black hole? A black hole is a region in space where gravity is so intense that nothing, not even light, can escape. At its very center is a point called the singularity, where mass is thought to collapse into infinite density. Surrounding it is the event horizon, the invisible boundary beyond which no information can return. Black holes aren't cosmic vacuum cleaners, though. They obey gravity just like any other massive object. If our sun were replaced with a black hole of the same mass, Earth would still orbit it, just in eternal darkness. Black holes form from dying stars. Not all stars become black holes, only the truly massive ones. When a star at least 20 times the mass of our sun exhausts its nuclear fuel, gravity wins. The star's core collapses under its own weight, and the outer layers explode in a supernova. What's left behind is either a neutron star, or, if dense enough, a black hole. In that instant, an object the size of a city might pack in more mass than 3 suns. The result? A place where time and space themselves twist into knots. The event horizon, the point of no return. The event horizon is the defining boundary of a black hole. It's not a physical surface, but a threshold in spacetime. Once crossed, nothing can escape. Not light, not sound, not even data. From the outside, it looks like a perfect, featureless black sphere. But inside, we believe space folds inward, directing everything to the singularity. Strangely, if you fell past the event horizon, you wouldn't feel anything special at that moment, but you'd be doomed to fall forever inward. Black holes come in different sizes. Black holes range from the relatively small to the truly massive. Stellar black holes, like the ones that form from stars, are a few kilometers across. Intermediate black holes are harder to find but may be thousands of times more massive than the Sun. Then there are supermassive black holes, monsters with masses of millions or even billions of suns, lurking in the centers of galaxies. Ours, in the heart of the Milky Way, is named Sagittarius A*, and it's over 4 million times the mass of our Sun. Black holes can merge. When 2 black holes orbit each other, they gradually spiral inward, losing energy through gravitational waves. Eventually, they merge into a single, more massive black hole. This collision releases an incredible burst of gravitational energy, literally ripples in the fabric of space and time. These events were predicted by Einstein, but only confirmed in 2015 by the LIGO detectors. It's like hearing the universe breathe for the first time. Time slows near a black hole. One of the strangest effects of black holes is time dilation. According to Einstein's theory of general relativity, gravity bends not just space but time. The stronger the gravity, the slower time moves. Near the event horizon, time slows dramatically. If you hovered just above it, an hour for you might be years for someone farther away. This isn't science fiction. It's been confirmed by observing clocks on satellites versus Earth. Nothing escapes, or does it? Stephen Hawking changed how we think about black holes when he proposed Hawking radiation. He suggested that black holes aren't truly black. Instead, they slowly emit tiny amounts of radiation due to quantum effects near the event horizon. Over unimaginable timescales, this could cause a black hole to evaporate completely. It's one of the few bridges between quantum physics and gravity, 2 theories that usually don't get along. Black holes warp light. Black holes don't just trap light, they bend it. Their intense gravity can distort space so much that light from stars behind them curves around the black hole, forming what's called an Einstein ring. These effects are part of a phenomenon known as gravitational lensing. In some cases, a single star or galaxy can appear in multiple places at once because its light is bent in different directions around a black hole. Falling in, what would it be like? If you fell into a small black hole, the tidal forces would stretch your body dramatically, a process scientists casually refer to as spaghettification. Your feet, being closer to the singularity, would be pulled much more strongly than your head. In a larger black hole, though, the gradient is gentler, and you might cross the event horizon without noticing, drifting peacefully into the unknown. Either way, once you're in, there's no coming back. Black holes shape galaxies. At the center of nearly every galaxy lies a supermassive black hole, and it plays a surprising role in galactic life. These giants don't just devour, they regulate. As matter falls in, they can eject powerful jets of energy and radiation that influence star formation across thousands of light years. In this way, black holes may act as both destroyers and creators, helping galaxies like our Milky Way take shape over billions of years. Black holes are invisible, but their shadows aren't. Black holes themselves emit no light, making them invisible against the backdrop of space. But the powerful gravity around them pulls in glowing gas and dust, creating a bright, swirling disk known as an accretion disk. The Event Horizon Telescope captured the first-ever image of a black hole's shadow in 2019, showing a glowing ring of light around a dark center, the silhouette of the black hole in the galaxy M87. This image confirmed decades of predictions and showed us the impossible made visible. Spin. Black holes can rotate. Black holes don't just sit still. Many spin rapidly. This spin, called angular momentum, affects the shape and behavior of the event horizon. A spinning black hole drags spacetime around with it in a process called frame dragging. In extreme cases, the spin can twist the event horizon into an oblate shape and create an ergosphere, a region outside the event horizon where energy can theoretically be extracted. Black holes can sing. Though space is silent, black holes can produce vibrations known as quasi-periodic oscillations. These are waves in the X-ray light emitted by hot gas orbiting close to the black hole's edge. Scientists have detected these songs or tones that reveal information about the black hole's mass and spin. Think of it as a cosmic lullaby, whispering secrets from the edge of oblivion. The closest known black hole is surprisingly near. For many years, astronomers thought the closest known black hole was thousands of light years away. But in 2020, they discovered one only about 1,000 light years from Earth, in our cosmic backyard. Named the unicorn because of its rarity and elusive nature, this stellar black hole provides a unique opportunity to study these mysterious objects up close. Black holes can evaporate over time. Though black holes are famous for trapping everything, they also slowly lose energy through Hawking radiation. This process takes an unimaginably long time, far longer than the current age of the universe for large black holes, but eventually they may disappear completely. This means black holes aren't eternal. They have a lifespan that stretches across cosmic eons. Wormholes and black holes. What's the difference? Popular science fiction often links black holes with wormholes, hypothetical tunnels through spacetime that could connect distant parts of the universe. While a black hole is a one-way trap, a wormhole, if they exist, might act as a shortcut through space. However, no observational evidence for wormholes exists yet. Black holes remain the mysterious one-way doors, inviting curiosity but not passage. The no-hair theorem. Black holes are surprisingly simple. Despite their complexity, black holes can be described by just three properties: mass, charge, and spin. This principle, called the no-hair theorem, suggests black holes don't reveal any other details about the matter that formed them. Once inside, everything becomes hidden, lost in the singularity, stripped down to these fundamental characteristics. Black holes could help us understand quantum gravity. One of the biggest puzzles in physics is uniting quantum mechanics and general relativity into a single theory. Black holes sit at the intersection of these two, where gravity is extremely strong and quantum effects matter. Studying black holes could unlock the secrets of quantum gravity, helping us understand how the universe works at its most fundamental level. Some black holes feed by pulling matter from companion stars. In binary star systems, a black hole may orbit closely with a normal star. The black hole's gravity can pull gas from its companion, creating a swirling accretion disk. As the gas spirals inward, It heats to millions of degrees and emits powerful X-rays detectable from Earth. These X-ray binaries offer astronomers valuable clues about black hole behavior. Black holes have inspired art, music, and imagination. Beyond science, black holes have captured the human imagination for decades. From paintings to movies like Interstellar, from music inspired by gravitational waves to poetic metaphors of the unknown, black holes symbolize mystery, power, and transformation. They invite us to ponder the infinite, to dream beyond our cosmic horizon. Black holes can grow by eating stars and gas. Black holes grow by pulling in nearby matter, stars, gas, dust, and even other black holes. When a star ventures too close, it can be ripped apart in a dramatic event called a tidal disruption event. The shredded material spirals inward, heating up and shining brightly before disappearing beyond the event horizon, feeding the black hole and sometimes causing brilliant flares visible across the universe. Supermassive black holes formed early in the universe. Supermassive black holes, with millions or billions of times the mass of the Sun, formed surprisingly early in cosmic history. Less than a billion years after the Big Bang. How these behemoths grew so quickly is still a mystery, but their existence shaped the formation of galaxies, influencing the cosmic web we observe today. Black holes can warp space like a funhouse mirror. The intense gravity of black holes doesn't just pull things inward, it bends the very fabric of space. This warping can distort the appearance of stars and galaxies behind them, stretching and magnifying their light in strange ways. This cosmic funhouse mirror effect reveals clues about the black hole's mass and location. The black hole at the Milky Way's center has a star orbiting it every 16 years. A star named S2 orbits our galaxy's central black hole, Sagittarius A*, every 16 years in a highly elliptical path. Tracking S2's movement has provided direct evidence of the black hole's mass and even tested Einstein's general relativity in extreme conditions. Black holes can be detected by gravitational waves. When massive black holes merge, they send ripples through spacetime known as gravitational waves. These waves were predicted by Einstein and first detected in 2015, opening a new way to hear the universe and observe phenomena invisible through traditional telescopes. The photon sphere is a halo of trapped light. Just outside the event horizon lies the photon sphere, a region where gravity is so strong that photons, particles of light, can orbit the black hole. This sphere forms a glowing ring, contributing to the black hole's eerie, shimmering appearance. Black holes can slow down or even reverse time for an outside observer. From a distance, objects falling into a black hole appear to slow down, their movements stretched out toward infinity. In theory, time near the event horizon almost stops, meaning an outside observer would never see something actually cross the point of no return, only an eternal freeze frame at the edge. Miniature black holes might exist. Some theories predict the existence of primordial black holes, tiny black holes formed in the early universe, much smaller than stellar black holes. While none have been definitively detected, they remain a fascinating possibility, potentially offering insight into dark matter and early cosmic conditions. The brightest known black hole beacon outshines its entire galaxy. Some black holes, known as quasars, actively consume vast amounts of matter and emit extraordinary amounts of light and radiation. These cosmic lighthouses can outshine all the stars in their host galaxy combined, visible billions of light-years away, shining as beacons from the universe's distant past. The study of black holes inspires advances in technology. Research into black holes has pushed technology forward, from advanced telescopes and detectors to algorithms analyzing gravitational waves. These innovations often find applications in medicine, data science, and even everyday electronics, proving that the study of the cosmos deeply benefits life here on Earth. Black holes can affect time on a cosmic scale. Black holes don't just bend space, they slow time itself. Around a supermassive black hole, time dilation becomes extreme. Near the event horizon, seconds can stretch into years when compared to a distant observer's clock. This effect has profound implications for how we understand time and reality itself. The spin of a black hole influences its energy output. A fast-spinning black hole can transfer rotational energy to its surroundings, sometimes powering powerful jets of particles and radiation that shoot out from its poles at nearly the speed of light. These jets can influence entire galaxies, suppressing or triggering star formation across vast distances. The information paradox. One of the greatest mysteries about black holes is what happens to information about the matter they consume. Quantum mechanics suggests information can't be destroyed, but black holes seem to erase it. This contradiction, known as the information paradox, challenges physicists and hints at new physics waiting to be discovered. Black holes can glow in X-rays and radio waves. While black holes themselves are dark, the matter falling into them emits intense radiation before crossing the event horizon. This radiation, often in X-ray and radio wavelengths, helps astronomers locate and study black holes millions or billions of light-years away. Supermassive black holes are the anchors of galaxies. Every large galaxy hosts a supermassive black hole at its center. These black holes anchor the galaxy's core, influencing the movement of stars and gas. The mass of these black holes is closely linked to the size and properties of their host galaxies, hinting at a deep cosmic connection. Black holes can cause gravitational lensing, magnifying distant objects. When light from a distant star or galaxy passes near a black hole, the intense gravity bends the light, magnifying and sometimes duplicating the image of the distant object. This gravitational lensing helps astronomers discover and study faraway parts of the universe. Some black holes are sleeping. Not all black holes actively consume matter. Many lie dormant, quietly lurking in space. Without nearby gas or stars to pull in, they emit little or no radiation, making them extremely difficult to detect, like cosmic ghosts drifting silently through the universe. The discovery of black holes revolutionized physics. Before black holes were widely accepted, many scientists considered them theoretical curiosities. Their discovery challenged fundamental ideas about space, time, and matter, and has pushed physics into new frontiers, including quantum gravity and string theory. The largest known black holes are gigantic. The biggest black holes, called ultramassive black holes, can have masses tens of billions of times greater than the Sun. These giants challenge current theories of black hole formation and growth, suggesting the universe still holds many cosmic secrets. Black holes are key to understanding the universe's evolution. By studying black holes, scientists gain insights into the formation of galaxies, the behavior of matter under extreme conditions, and the nature of space and time itself. Black holes act as cosmic laboratories, helping us understand how the universe began, evolved, and where it might be headed. Black holes can be part of binary systems. Some black holes orbit closely with companion stars in binary systems. These cosmic duos can reveal black hole properties through their gravitational dance and the intense X-rays emitted as the black hole pulls matter from its partner. The shadow of a black hole reveals its shape. The dark silhouette seen in black hole images is called the shadow. Its size and shape reveal details about the black hole's mass and spin, acting like a fingerprint for these enigmatic giants. Black holes can influence star formation. Jets and winds from active black holes can both trigger and suppress star formation in surrounding gas clouds, making them important cosmic regulators in the life cycle of galaxies. The first gravitational waves detected were from black hole mergers. In 2015, the LIGO Observatory recorded gravitational waves from two merging black holes, opening a new era of astronomy that listens to the cosmos rather than just observing light. Black holes can have powerful magnetic fields. Some black holes generate intense magnetic fields near their event horizons, affecting the motion of particles and the formation of jets that can extend for thousands of light-years. Black holes can evaporate through Hawking radiation. Though incredibly slow, black holes emit particles and energy in a process predicted by Stephen Hawking, meaning they aren't permanent but will fade away over unimaginable timescales. The size of a black hole's event horizon grows with mass. The radius of the event horizon, called the Schwarzschild radius, scales linearly with mass. So, a black hole with 10 times the mass of our Sun has an event horizon 10 times wider. Some black holes form in star clusters. Dense clusters of stars can produce black holes through repeated stellar interactions and mergers, making them cosmic laboratories for black hole formation. Black holes may be connected to dark matter mysteries. Some theories suggest primordial black holes might make up some or all of the universe's dark matter, the invisible substance that holds galaxies together. Studying black holes advances technology. Efforts to understand black holes have driven advances in computing, data analysis, and imaging techniques that have applications beyond astronomy, including medicine and communications. Black holes as cosmic time machines. Black holes don't just distort space, they also warp time in extraordinary ways. When you approach a black hole, gravity's grip grows so intense that time itself slows down relative to an outside observer. This phenomenon, known as gravitational time dilation, means that if you were near a black hole's event horizon, seconds for you could stretch into years for someone watching from afar. This incredible slowing of time isn't just theoretical. It's a direct consequence of Einstein's theory of general relativity and has profound implications for how we understand the flow of time in our universe. Near a black hole, time can almost stand still, creating a kind of cosmic time capsule where moments stretch endlessly. The spin of black holes warps space around them. Not all black holes are static. Many spin at incredible speeds, dragging the very fabric of spacetime around with them in a process called frame dragging. Imagine the black hole as a cosmic whirlpool, twisting everything in its vicinity. This rotation alters the shape of the event horizon, making it oblate rather than perfectly spherical, and creates a region called the ergosphere, where space-time is dragged so strongly that nothing can remain still. This spin doesn't just influence nearby matter. It can power enormous jets of energy that shoot out along the black hole's poles, sometimes stretching for thousands of light years. These jets affect not only the immediate environment but entire galaxies, influencing their evolution over billions of years. The mysterious information paradox challenges our understanding of physics. One of the deepest mysteries in black hole physics is the information paradox. According to classical physics, anything that falls into a black hole is lost forever. But quantum mechanics insists that information cannot be destroyed. This apparent contradiction puzzles scientists. When matter is swallowed by a black hole, what happens to the information it contains? Does it vanish, violating the laws of quantum theory? Or is it somehow preserved and encoded in the black hole's event horizon, or emitted through subtle quantum effects? This paradox hints that our current understanding of physics is incomplete and points toward a revolutionary theory that could unite quantum mechanics with gravity, a quest that continues to inspire physicists around the world. Black holes illuminate the cosmos with X-rays and radio waves. Though black holes themselves emit no light, the intense gravitational forces in their vicinity cause nearby matter to heat up to millions of degrees. This hot, glowing gas forms an accretion disk around the black hole, radiating powerful X-rays and radio waves that astronomers detect from Earth. These energetic emissions allow us to identify and study black holes across the universe, even those too far away or too faint to observe directly. Through this radiation, black holes become cosmic beacons, revealing not only their presence but also offering clues about their mass, spin, and the environment around them. It's a paradoxical light born from darkness, illuminating some of the most extreme corners of space. Supermassive black holes anchor the hearts of galaxies. At the center of nearly every large galaxy lies a supermassive black hole, with masses ranging from millions to billions of times that of our Sun. These giants act as cosmic anchors, holding galaxies together and influencing the movement of stars and gas throughout their vast reaches. The mass of these black holes is closely correlated with the size and behavior of their host galaxies, suggesting a deep and mysterious connection. Their gravity can regulate star formation by feeding on gas or blasting it away with intense radiation and powerful jets, shaping the very structure of the galaxy over billions of years. In many ways, supermassive black holes are the invisible architects of cosmic evolution. Gravitational lensing, black holes as cosmic magnifying glasses. The powerful gravity of a black hole doesn't just trap matter, it also bends light. This bending causes an effect known as gravitational lensing, where light from distant stars and galaxies is curved and magnified as it passes near a black hole. This cosmic magnifying glass can distort, duplicate, and brighten images of objects behind the black hole, providing astronomers with a unique tool to study galaxies billions of light-years away. Sometimes, this lensing creates stunning visual phenomena like Einstein rings, where the background light forms a perfect circle around the black hole's shadow. Through gravitational lensing, black holes offer us glimpses into the distant, early universe. Black holes often lurk in quiet darkness. While some black holes are fierce cosmic engines, actively consuming matter and emitting bright radiation, many lie dormant, invisible and silent in the vastness of space. These sleeping black holes have no nearby gas or stars to pull in, so they emit little to no detectable light or radiation. Detecting these quiet black holes requires indirect methods, such as observing the gravitational influence they exert on nearby stars or gas clouds. This hidden population of black holes drifts like cosmic ghosts, silently shaping the dynamics of galaxies without announcing their presence. The discovery of black holes revolutionized our understanding of the universe. Black holes were once theoretical oddities, predicted by Einstein's equations but met with skepticism by many scientists. Over the decades, however, observations have confirmed their existence, challenging long-held notions about space, time, and matter. Their discovery has pushed physics into new frontiers, requiring us to rethink fundamental concepts about gravity and quantum mechanics. Black holes have become a testing ground for theories of the universe, offering insights into the nature of reality itself, and inspiring new technologies and methods of observation that extend far beyond astronomy. Ultramassive black holes defy our understanding of growth. Some black holes are so massive that they challenge existing models of how black holes form and grow. These ultramassive black holes, tipping the scales at tens of billions of solar masses, are found at the centers of giant galaxies and galaxy clusters. Their enormous size suggests they grew rapidly through mergers and accretion in the early universe, but exactly how they reached such colossal proportions remains a mystery. Studying these giants helps scientists probe the limits of black hole physics and the cosmic processes that shape the large-scale structure of the universe. Black holes are cosmic laboratories for understanding the universe. Because black holes create conditions so extreme that matter, energy, space, and time behave in extraordinary ways, they serve as natural laboratories for scientists. Studying black holes allows physicists to explore the frontiers of general relativity, quantum mechanics, and high-energy astrophysics. Observations of black holes inform theories about the birth and death of stars, the evolution of galaxies, and the fundamental laws governing the cosmos. In many ways, black holes are not just cosmic mysteries. They are keys unlocking the deepest secrets of our universe. Black holes can have complex magnetic fields shaping their surroundings. Though black holes themselves are regions where gravity dominates, the swirling disks of plasma around them generate some of the most intense magnetic fields in the universe. These magnetic fields twist and coil, channeling charged particles into narrow jets that blast away from the black hole's poles at nearly the speed of light. These jets can stretch for thousands of light-years, interacting with the gas and dust in their host galaxies, sometimes triggering bursts of star formation or clearing regions entirely. The dance between gravity and magnetism near black holes is a powerful force shaping the cosmic environment on grand scales. The event horizon defines the point of no return. The event horizon is often called the surface of a black hole, though it's not a physical boundary but a mathematical one, the point beyond which nothing can escape the black hole's gravitational pull, not even light. From the perspective of a distant observer, objects approaching the event horizon appear to slow down and freeze, fading as their light redshifts to invisibility. This horizon marks the limit of our observable universe inside the black hole, hiding all that lies beyond it from view and challenging scientists to understand what happens inside this mysterious boundary. The concept of spaghettification explains what happens near a black hole. One of the most mind-bending effects near black holes is the tidal force gradient, which stretches objects lengthwise and compresses them laterally, a process whimsically called spaghettification. Imagine falling feet first toward a black hole. The gravitational pull on your feet is much stronger than on your head, elongating you into a thin strand of matter. Though this sounds terrifying, the effect varies depending on the black hole's size. For supermassive black holes, this stretching happens closer to the event horizon, giving you a chance to cross it before spaghettification becomes extreme, unlike smaller black holes where it occurs well outside the horizon. Black holes emit Hawking radiation, slowly evaporating over time. Contrary to the idea that nothing escapes a black hole, Stephen Hawking proposed that black holes can emit particles due to quantum effects near the event horizon. This Hawking radiation causes black holes to slowly lose mass and energy, evaporating over unimaginably long timescales. For large black holes, this process is incredibly slow, but for tiny black holes it would happen much faster. Though Hawking radiation has not yet been directly observed, it offers a vital link between quantum mechanics and gravity and remains a key area of theoretical research. Black holes form from the collapse of massive stars. Most black holes originate from the death throes of massive stars. When a star much larger than our Sun exhausts its nuclear fuel, it can no longer support itself against gravity and collapses under its own weight. If the remaining core's mass is sufficient, typically more than about 3 times the Sun's mass, it crushes itself into a singularity, forming a black hole. This dramatic transformation marks the end of the star's life and the birth of one of the universe's most enigmatic objects. Binary black hole systems are cosmic dance partners. Some black holes exist in pairs, locked in a gravitational dance known as binary black hole systems. These pairs orbit each other, spiraling closer over time as they emit gravitational waves, ripples in the fabric of spacetime. When they finally collide and merge, they release enormous amounts of energy detectable across the universe. Observing these mergers has opened a new window into black hole physics and helped scientists measure fundamental cosmic properties like the expansion rate of the universe. Black holes can warp light to create stunning visual phenomena. The extreme gravity near black holes bends light paths dramatically, causing fascinating optical illusions. Light from stars behind a black hole can be bent into arcs, rings, or even multiple images, a process called gravitational lensing. Sometimes, this effect creates nearly perfect circles of light, known as Einstein rings. These visual distortions not only provide beautiful cosmic spectacles but also help astronomers map the distribution of matter in the universe and study objects billions of light-years away. Sagittarius A, our galaxy's central black hole, is quiet but massive asterisk. At the heart of the Milky Way lies Sagittarius A asterisk, a supermassive black hole about 4 million times the mass of our Sun. Unlike some active black holes that blaze with radiation, Sagittarius A asterisk is relatively quiet, consuming matter slowly and emitting faint signals. Despite its quiet nature, its gravitational influence is profound, shaping the orbits of stars near the galactic center and anchoring the Milky Way's structure. Studying Sagittarius A asterisk gives us a closer look at the nature of supermassive black holes in typical galaxies. Black holes influence the evolution of galaxies. Far from being mere cosmic oddities, black holes play an essential role in the life cycle of galaxies. Through powerful jets and radiation, active black holes regulate the growth of their host galaxies, sometimes triggering bursts of star formation by compressing gas or, conversely, blowing gas away and shutting down star formation entirely. This feedback process is crucial for shaping the size, structure, and star population of galaxies, making black holes key players in cosmic evolution. The Event Horizon Telescope took the first image of a black hole. In 2019, the world witnessed a historic breakthrough, the first-ever image of a black hole's event horizon, captured by the Event Horizon Telescope, EHT. This global network of radio telescopes combined observations from around the world to create a detailed picture of the black hole in the galaxy M87. The glowing ring and dark shadow seen in this image confirmed decades of theoretical predictions and marked a milestone in our ability to observe the invisible, deepening our understanding of these cosmic enigmas. Black holes can merge to form even larger giants. When two black holes collide, their immense gravitational fields cause them to spiral inward and eventually merge, creating a single, more massive black hole. This cosmic union releases vast amounts of energy in the form of gravitational waves, ripples in the fabric of spacetime, that can travel billions of light-years. These mergers shape the growth of black holes across the universe, building up the supermassive giants that anchor galaxies, and they offer a rare glimpse into the most violent, energetic processes known to physics. The singularity is a point of infinite density. At the core of every black hole lies the singularity, a point where matter is crushed to infinite density and volume shrinks to zero. This extreme compression warps space and time beyond comprehension and is where known laws of physics break down. The singularity represents the ultimate frontier of scientific understanding, a mysterious region that challenges our grasp of reality and demands new physics to explain what truly happens in this cosmic abyss. Black hole jets can travel across intergalactic space. Powerful jets emitted from black holes don't just impact their home galaxies. They can shoot energetic particles thousands or even millions of light-years into intergalactic space. These jets carry enormous amounts of energy and can heat or compress gas clouds far from the black hole, influencing galaxy formation and the evolution of cosmic structures on the largest scales imaginable. Black holes can be detected by their effects on nearby stars. Even invisible black holes leave clues about their presence. When a black hole shares a system with a star, its gravity can pull on the star, affecting its motion in measurable ways. By tracking the orbits and speeds of these stars, astronomers can infer the presence and properties of hidden black holes, revealing these invisible giants through their gravitational footprints. Some black holes may have formed primordially, soon after the Big Bang. Not all black holes are remnants of dying stars. Some theories suggest that tiny primordial black holes could have formed from density fluctuations in the extremely hot, dense conditions shortly after the Big Bang. These ancient black holes might vary in size, and some could even contribute to the mysterious dark matter that makes up much of the universe's mass, offering exciting possibilities for future discoveries. The gravitational pull near a black hole is the strongest known. Nothing in the universe exerts a gravitational pull as intense as a black hole's event horizon. This gravity is so powerful that it overcomes all other forces, pulling in anything that ventures too close, including light itself. This overwhelming force defines the black hole's ability to trap everything and shapes the extreme physics happening near it. Black hole accretion disks can reach incredible temperatures. The swirling disks of gas and dust spiraling into black holes are among the hottest places in the universe. Friction and gravitational forces heat the matter to millions of degrees, causing it to glow brightly in X-rays and other high-energy radiation. These glowing disks not only provide a window into black hole environments but also play a crucial role in how black holes grow over time. Black holes can slow their spin over time. As black holes consume matter and merge with others, their spin rates can change. Sometimes, the chaotic inflow of matter can slow a black hole's rotation, while in other cases, the momentum from accreted material or merging black holes can spin it up to near the speed of light. This changing spin affects how energy is released and how the black hole interacts with its surroundings. The no-hair theorem simplifies black hole properties. Despite their complexity, black holes are surprisingly simple in terms of the information they carry. According to the no-hair theorem, black holes can be fully described by just three properties: mass, electric charge, and spin. This means all other details about the matter that formed them or fell inside are lost from an outside observer's perspective, highlighting the mysterious nature of their event horizons. Black holes challenge our concepts of space and time. By warping space and time to their limits, black holes challenge our fundamental understanding of the universe. Near them, space can stretch, time can slow, and causality can break down, pushing the boundaries of physics. Studying these extreme objects helps physicists develop new theories, such as quantum gravity, that aim to unify the known forces and explain the deepest workings of reality. Black holes can create gravitational echoes in spacetime. When black holes merge or undergo sudden changes, they can create ring-down vibrations, like ripples after a bell is struck, that travel through spacetime. These gravitational echoes carry unique signatures, allowing scientists to test the nature of black holes and the validity of Einstein's theory in extreme environments. Listening to these cosmic vibrations helps unlock secrets about what happens in the moments after black hole mergers. Black holes can influence the shape and movement of entire galaxies. Supermassive black holes at galactic centers exert a gravitational pull that shapes star orbits and the motion of gas clouds. Over billions of years, this influence sculpts the structure and rotation of galaxies, contributing to their spiral arms or elliptical shapes. This cosmic choreography is a dance between gravity, angular momentum, and black hole feedback, weaving the tapestry of galaxies we see across the universe. Black holes could help answer the question of what came before the Big Bang. Some theoretical models propose that black holes might act as gateways to other universes or that the singularity within could be linked to a previous cosmic cycle. These ideas, though speculative, push the boundaries of cosmology and invite us to ponder whether black holes could hold clues about the origin of our universe and the possibility of multiverses beyond our perception. Black holes affect time dilation for observers nearby. If you were to hover near a black hole without crossing the event horizon, time for you would pass much more slowly compared to someone far away. This extreme time dilation means you could witness distant cosmic events unfolding rapidly while your own time crawls. Such effects, predicted by relativity, show how black holes stretch our understanding of time and its relativity. Black holes can trap magnetic fields in their accretion disks. The plasma spiraling into black holes drags magnetic fields along, trapping and amplifying them near the event horizon. These intense fields can twist and snap, releasing bursts of energy and contributing to the launching of jets. Understanding these magnetic processes is key to explaining the high-energy phenomena often observed near black holes. Black holes can form in star clusters through stellar collisions. In dense star clusters, frequent close encounters and collisions between stars can lead to the formation of black holes. These black holes can then merge with each other, gradually growing more massive. Such environments serve as cosmic breeding grounds for black holes and help explain their population in various regions of the universe. The dark shadow seen around black holes is caused by photon orbits. The glowing ring seen in black hole images, like the one captured by the Event Horizon Telescope, surrounds a dark shadow created by photons trapped in unstable orbits near the event horizon. This photon ring is a boundary where light orbits the black hole multiple times before escaping or falling in, creating the striking image of a glowing halo around darkness. Black holes can influence star formation by clearing or compressing gas clouds. Jets and radiation from active black holes can either blow away gas clouds, preventing new stars from forming, or compress gas enough to trigger bursts of star formation. This dual role means black holes act as cosmic regulators, balancing the birth and death of stars and influencing the growth and evolution of galaxies. Intermediate mass black holes fill the gap between stellar and supermassive black holes. Between the well-known categories of stellar mass and supermassive black holes lies a mysterious class called intermediate mass black holes. Though harder to detect, these black holes are thought to play a crucial role in galaxy formation and may represent a missing link in black hole evolution, bridging the gap between small and colossal black holes. Studying black holes helps scientists explore quantum gravity. Black holes challenge the current understanding of physics because they involve both the incredibly massive, gravity, and the incredibly tiny, quantum effects. Scientists study black holes to develop a theory of quantum gravity that merges general relativity with quantum mechanics, aiming to uncover a deeper, unified description of the universe's fundamental forces. Black holes can spin near the speed of light. Some black holes rotate incredibly fast, with their spin approaching the speed of light. This rapid spin drags spacetime around with it, a phenomenon known as frame dragging. Near these spinning black holes, space itself is twisted, affecting how matter and light behave in their vicinity, and creating extreme environments that push the limits of physics as we know it. The surface gravity of a black hole is immense. The gravity experienced just outside a black hole's event horizon is unimaginably strong. It can pull objects with forces trillions of times stronger than Earth's gravity. This intense pull shapes the dynamics of infalling matter and causes the extreme effects that make black holes unique, including time dilation and the trapping of light. Black holes could potentially power future space travel concepts. Some futuristic theories suggest that the immense energy around black holes, such as from their accretion disks or jets, could one day be harnessed as an energy source for advanced space travel or communication. Concepts like the Penrose process describe how energy can be extracted from a rotating black hole, hinting at possibilities far beyond our current technology. The cosmic censorship hypothesis suggests singularities are hidden. Physicists propose that singularities formed inside black holes are always hidden behind event horizons, preventing naked singularities that could expose these infinitely dense points to the universe. This cosmic censorship hypothesis preserves the predictability of physical laws and ensures that singularities don't disrupt the universe's causal structure. Black holes can influence cosmic microwave background radiation. Some scientists theorize that primordial black holes could have subtly influenced the cosmic microwave background, the afterglow of the Big Bang, by affecting the distribution of matter and energy in the early universe. Studying these effects might reveal new clues about the universe's infancy and the role black holes played in shaping it. Black hole thermodynamics links gravity and heat. Surprisingly, black holes obey laws similar to thermodynamics. They have entropy and temperature, radiate energy, and evolve according to predictable rules. This analogy connects gravity, quantum mechanics, and statistical physics, hinting at a deep and fundamental unity in nature's forces that scientists are still striving to understand. Black holes can bend and stretch space to create wormholes. Theoretical physics suggests that black holes could form wormholes, shortcuts through spacetime that connect distant regions of the universe. While purely speculative, these structures, if they exist, might allow for faster-than-light travel or even time travel, sparking imagination and scientific inquiry into the ultimate nature of space and time. Observing black holes tests Einstein's general relativity in extreme conditions. Black holes serve as natural laboratories for testing Einstein's theory of general relativity under the most extreme conditions. Precise measurements of how light bends, time slows, and gravitational waves propagate near black holes either confirm Einstein's predictions or point to new physics, helping refine our understanding of gravity. Black holes may eventually evaporate completely over trillions of years. Thanks to Hawking radiation, black holes are not eternal. Over incomprehensibly long timescales, far exceeding the current age of the universe, they slowly lose mass and evaporate away. This slow fading marks a cosmic cycle, reminding us that even the most powerful forces are transient in the grand scheme of cosmic time. Black holes inspire wonder and drive scientific discovery. Beyond their scientific significance, black holes captivate our imagination and symbolize the unknown frontiers of the universe. Their mysteries fuel exploration, inspire art and philosophy, and remind us of the profound beauty and complexity of the cosmos. Studying black holes is not just about physics, it's about expanding humanity's quest to understand our place in the vast, mysterious universe. As we drift away from the enigmatic depths of black holes, remember that these cosmic giants are more than just mysterious voids, they are gateways to understanding the universe itself. Each fact we've explored tonight reveals just how incredible and intricate our cosmos truly is, blending the boundaries of time, space, and reality. So, as you gently close your eyes, let the vastness of space and the quiet power of black holes lull you into peaceful rest, knowing that the universe is full of wonders, waiting patiently for you to discover them. Thank you for joining this cosmic journey. Sleep well, and may your dreams be as infinite as the stars.